Professor Shin is actually an associate professor at Aju University in South Korea. He's a senior member of the IEEE. He's a faculty member. He was a faculty member at the Busan National University from 2018 to 2021. He received his bachelor degrees and the master degrees from KAIST in South Korea in 2005 and 2007, respectively, and his PhD from Seoul National University in 2017. From 2007 to 2014, he was a technical staff at Samsung AIT and Samsung's Electronics in South Korea. From 2016 and to 2018, he was a doctoral research fellow and visiting scholar at Princeton University in the US. He got several awards, very prestigious awards. I think it's, let's make it short. I think one of the most interesting ones is that he got this Asia Pacific Outstanding Young Research Award from the IEEE ComSoc Society, which is very prestigious. He got the Best PhD Dissertation Award in 2017 and many more, contents and so on. So it's a pleasure basically to listen to the talk basically. So I'm looking forward to you. Before I hand over to Professor Shin, let me just talk shortly about the rules. Basically, we are going to have the talk now for around like 50 minutes, during which you are going to be muted, and you will be asked basically to ask your question via the chat. And then the Q&A session, which is going to be roughly 10 minutes. Basically, you can raise your hand, and then we will unmute you basically to raise your questions. And then, of course, depending on the number of questions appearing basically, which we might take 2 to 5 questions from the chat. Okay. Then, without further ado, I hand over to Professor Shin. Wonjae,
okay,
scene is yours.
Thank you, Aydin. So yeah. So I'm going to share my screen. So did you see my full screen?
Yes, looks good.
Okay, thank you. Right, so thank you, Aydin, for your nice introduction. So okay, so welcome to my talk for the RSMA webinar series. Yeah, my name is Wonjae Shin from Aju University, but now I'm visiting Bruno Group at Imperial College London, so I'm in London now. So today I'm going to talk about RSMA, but particularly on how we can make use of RSMA in the context of this satellite communications or integrate satellite communication network. So this is what I'm going to talk about today. First of all, so we will start with some key motivation of the satellite communication for 6G. Then we will see the technical challenge and some research issue on satellite communications. Finally, we jump into the robust beam design for satellite communication and how it works in various satellite communication scenarios. So why do satellite become very essential component for 6G? So let me start with some underlying trend of the wireless communications. So since 1980s, so wireless communications have been evolved by increasing the user data rate 10 to the 100 times in each generations due to the emergence of new services here. So now we are in just between the 4G and 5G, and to support upcoming ultra broadband and massive IoT connectivities, the 5G network are expected to offer data rate up to the 100 times faster than current 4G network. Beyond this, 6G is envisioned to support even more diverse application with a very different requirement. One of them would be the global service coverage to fill out all the coverage all of the world. So with this, 6G will be realize hyperconnectivity society in near future. So here's some supporting data for the coverage imbalance all of the world. So this is a 2G coverage and 3G and 4G. So this is accumulate coverage map. And very interesting, if according to ITUR report, only 50% of the global population use a mobile internet. Although this is a 2018 result, but yeah, the situation is getting much better through the COVID era, but still, I mean, in 2022 in US, more than 20% of the area is remain uncovered by wireless company in US. So a lot of still there are a lot of the coverage hole to fill out. So to tackle these issues, the coverage hole, I mean, dead zone problem, so use of the non-terrestrial network would be a very promising solution. Why? This is because one in the sky or space will have a much wider beam coverage compared to existing terrestrial network. So we can make use of the non-terrestrial network, including HAPS and LEO and GEO, to expand the coverage above and beyond. So those are the role of the satellite for the future network. So first one should be to extend coverage in unserved and underserved coverage for the service ubiquity. And second one would be to improve the user experience for the IoT or onboard moving platform. And third, but not the least, the multicast and broadcast would be a very important role for the satellite communication. It can broadcast the message in a very efficient manner. So those are some usage case for the satellite communication for the future communication. So it's not only for the remote area, but also in the urban area. So you can see that there are lots of the variety of the application in using the satellite. Okay, so not only for coverage extension, it also have some kind of the wireless backhauling or a broadcast popular contest or connected car or aeronautical broadband or the emergency and the safety issue. So here's some key terminology for the satellite communications. So satellite communication is typically composed of three different the entities. First one is the gateway, second one is satellite, and third one is user terminal. So feeder link, they connect the gateway with a satellite, whereas the user link, they connect the satellite with the user terminals. So concatenation of the feeder link and user link is called the forward link, and reverse link is called the return link. So let's keep this terminology in mind while in this talk. So let me move on to satellite spectrum. So due to shortage of the satellite spectrum, satellite operator moving from conventional the C-band or S-band or Ku band to the Ka or even higher bandwidth. But things are not very quite easy, because for the higher bandwidth, usually the Ka band are much more susceptible to adverse weather condition compared to lower band. On the other hand, the moving to the higher frequency allow for some smaller antenna size, that promoting the use of multi-antenna system or the beamforming. So in addition, the Starlink, they think about even higher frequency band for the feeder link, because the feeder link are very stable, and also hot gateway should have a very large hardware size, so it can manage it for the high path loss. So there are some pros and cons for the different frequency use, but still, I mean, there are a lot of issues for the shortage of the frequency band for the satellite communications. So this is a paradigm shift for the usage of how to use satellites. So typically, we use a fixed satellite service. So it's have a very large coverage on the ground. So, but this architecture is so for the broadcast message or the TV signal, because it broadcasts the signal to very wide area. But on the other hand, for the communication purpose, high throughput satellite, so-called HTS satellite, receive lots of attention these days. So satellite forms the multiple narrow beams here, or spot beam. So each spot or the circle here so formed by the beam of the satellite. And here there are multiple spot beam here, and each spot beam inside serve more than one user simultaneously. So if you think about aggressive frequency reuse across a multiple spot beam, of course, you have a higher level of the interference due to the such a side lobe of the beams here. So there are different types of satellite. So according to the altitude, we can classify satellite into three different categories. The first one is GEO, and second one is MEO, and third one is EDIO. So GEO is quite stationary in relation to the Earth. So the orbital period is 24 hours, while EDIO has only the half an hour for the orbital period. Because it's a very fast movement at 7.5 kilometers per second at 600 kilometer altitude. So if you look at the left curve, so as the altitude increase of the satellite, it might have a better coverage. So you may think that GEO might be the best solution. But the problem is, if you look at the red curve with a right axis, this is the latency for the round trip delay. So of course, as the altitude is getting higher, then round trip delay must be getting increased, right? Due to the propagation delay. So according to the VoIP company like a Cisco, the 150 millisecond would be the normal latency for the VoIP. So you can realize that only EDIO can provide some, EDIO can provide some LTE like a latency communication. So these are the reason why this day the EDIO satellite are getting a lot of attention for 6G. And so it has a lot of the pros and cons. So it's also, EDIO can provide a low latency and a low transmit power and small size. Also, its manufacturing and launching costs are comparably lower than GEO, MEO, thanks to some reuse of rocket by the SpaceX. But still, there are lots of issues. So it's because it has a very low altitude. So compared to GEO or MEO, it might have a very small coverage. So to cover global connectivity using EDIO, it might have some massive cancellations with help of the intersatellite link. Moreover, the short visible time and huge Doppler effect should be also tackled due to the fast movement of the EDIO satellite. Okay, so there are lots of issues still. But still, I mean, many EDIO satellite operator already start to launch their satellite to form their massive constellations. So with target of 42,000 satellite, the SpaceX already launching in 2019, and OneWeb and Telesat and Amazon also, they are in the process of being complete for with their own target. So in 3GPP also try to work on the standardization of the non-terrestrial network with emphasis on EDIO, especially. So, so at the beginning, they usually work on independently just the standard satellite or the terrestrial network. But in the end, they're gonna have a look at the unified design of satellite and terrestrial network. This is the recent trend. So let's see what is technical challenge of the satellite communications. So key feature of satellite comm is twofold. So first one is multicast transmission. So this this might be a change in the near future, but if you look at a modern and the latest standard of the satellite communication called DVB-S2X, so transmission is based on frame-based recording. So what is frame-based recording? It's multiplex data of all the users belong to the same beam are encoded by the single long code word to cope with the large fading loss and as well as to increase of encapsulation efficiency. So this is a multicast message. So the message should be decoded by the group of users in belong to the same beam. And another key feature should be the multi-beam transmission, as I mentioned earlier. So effectively the system especially the user link looks like the multi-group multicast transmission. So this the group here, each group represent the one beam here, right? So, and here are some key challenges. So if you use aggressive frequency reuse across the multiple spot beam, so you have a higher level of interference or inter-beam interference, I mean. And also should be depending on how many users you consider in each beam, but it's typically the satellite scenario should be the user overloaded cases in which the number of users is much larger than the antennas or the feed element. Yeah, feed is the same as antennas in our terminology. And also it has the high propagation delay so that it's hard to get accurate channel feedback in Korean time. So this is also a very important issue. And also time domain variation of the channel should be very significant, especially for the ADO cases. So with this, imperfect CSI at the transmitter or gateway or satellite should be a very natural assumption. So it's so usually the I mean it's in case of satellite, yeah, for purpose of inference management. This, let's move on discussion on why enough to handle these challenges. So as I mentioned earlier, the satellite scenario is overloaded cases because of the multi-group multicast transmission. This thing pre-coder design are very sensitive to the number of users in terms of the number of antennas that the satellite have. So it's hard to, it's challenged to handle all the interference in this scenario. More knowledge of CSIT is, it should be also depending on which kind of the satellite you use. GEO, the channel might not be varying very fast, but feedback delay long. It's about 500 milliseconds for the round trip delay. So it's so the time you get feedback information is already outdated. And for ADO case, the feedback delay is not that long, but channel pretty fast due to this high fast movement. So also easily the CSIT information should be easily outdated. But the problem is linear line on the heavily relying on this. So we think we have to with some robust and flexible multiple access called the RSMA for a design of the satellite. Right. So let's move on some robust multi-beam design for satellite communications. So before going to details, yeah, let's review the RSMA fundamentals, which is our building block. So the user splitting, multiple access.
So for interrupting, Wonjae, the connection seems to be Not pretty good. So
Oh,
maybe can you switch off your camera?
oh,
So maybe it's better then.
okay, okay. So I just switch off on my camera. So is that better or?
It looks to be good now. So let's go ahead. Oh, I think we lost him, right?
Yeah, I think he will connect back.
Okay. There he is. Okay. Wonjae, are you back? You're muted.
Oh, okay. I'm back. So
Okay,
yeah.
great. Yeah.
So my wireless connection is not very good here. Maybe the satellite should be required in
Yes.
this London as well. Yeah.
Okay, great. Yeah, yeah,
Okay.
please proceed. Sorry.
Okay, I no problem. Thank you for letting me know. Yeah. So yeah, before going to details of the proposed one, let's review the RSMA fundamentals for because this is our building block. Yeah, so this is a architecture of the K-user rate splitting multiple access. And what we want to do here at the transmitter side is split the message into the two part, the private and common part, like this. So a group of the common message here want to be decoded by the all users. So we can make those group of message as a single common message like this. So common message can be recovered by the all users, and then private stream can be recovered by corresponding users only. So here, one thing I want to note that here is, although common message is decoded by the all users, but it's not necessary to intended for the all users. So which is not a multicast message. Yeah, but why we come up with the common message is for purpose of the interference management. So let's see the relationship between the RSMA and other multiple access by looking at the two user example here. So so the difference between the RSMA and NUMA or SDMA is how the message are splitted. So for RSMA, as I mentioned earlier, each users is split into two parts. The one's common and the other one is private. But if you look at the NUMA, we allocate the message of strong user into the private, while the weaker user message is allocated the common message. So yeah, so the common message should be decoded by the both user. On the other hand, in SDMA, both users are transmit as a private message. So yeah, we do not allocate any common information here in this case. So by adjusting how much common information we put, rate splitting can boil down NOMA or SDMA, as well as multicast and OMA. So this leads us to conclude that RSMA can be a generalized multiple access scheme. Right. So as for the receive operation of the RSMA, both users first decode common signal by treating private signal as noise. And after that, yeah, each user perform SAC and try to retrieve each private message. So in essence, RSMA can partially decode interference and partially treat interference as noise, not like SDMA or NOMA. So another motivation of RSMA is it's a promising MIMO solution with imperfect CSIT. So last 20 years, most of the information theory's limit has been discovered, provided kind of the perfect CSIT is available. But in case of the imperfect CSIT, it doesn't have a much optimality claim. However, RSA turns out to be optimal in the sense of degree of freedom, which is a high ISNR characteristic of the capacity. So its pre-coders optimization involve not only the private message, but also the common message. So that's a new approach for the RSMA. So those are the degree of freedom reason with imperfect CSIT for 2-user cases. But it turns out we cannot reach any better degree of freedom than this blue curve achieved by the RSMA. So this is an illustration of where robustness of RSMA come from. So this is a channel model, and the error comes in a CSIT. So this the average power of the error can follow the p to the minus alpha, and then p is the transmit power, and alpha is related to the number of feedback bits. So if the alpha is greater than 1 or equal to 1, then we can manage the interference very well, because p goes to infinity, then the error goes to a very small number. But the problem happens when alpha is between 0 and 1, then the interference level is not as similar as a noise, so it might have some problem. So if the interference cannot be eliminated or reduced to the noise level due to the no CSIT portion, why not decode it and remove it from the received signal in part with a portion of the perfect CSIT? So this is why the rate splitting comes in. So we can decompose into superposition of 2 subnetwork with a perfect or no CSIT. And then the SDMA can provide some synergetic gain, synergetic degree of freedom gain, like this. And in the end, this degree of freedom gain can translate into the rate gain as well, as we expect. So we can claim that RSMA can achieve the higher sum rate while reducing feedback. With some limited feedback. Right, so let's see how we can apply the RSMA in the context of the satellite. So this is a multi-beam channel model, which is time-varying equivalent channel vector between the satellite and the ith user here. So H is composed of the RT, which is the time-varying range attenuation between a satellite and the users. And CI is a constant factor collecting all the deterministic link budget parameter. And BI is a satellite antenna gain of the ith beam. And zeta I is the vector of the phase component of the channel, including phase noise introduced by the local oscillator. So RT here, specifically RT here, the range fadings follow log normal distribution. On the other hand, in other words, range attenuation in dB scale follow log normal distribution. Okay. So this is a well-known assumption. And in the satellite society, and deterministic link budget parameter is also a function of some frequency and receiver gain and noise power. So this is the beam gain. So beam gain is mostly depending on where the users are located in its beam. So if the users are located cell or beam edge, of course, it might have a much less gain than one it has in center of the beam, right? So it's modeled by this relative position. So here, this is the model for the very first work of the RSMA-based multi-beam satellite channel proposed by Longfei and Bruno at Imperial College. So if we have a K users served by the M multicast satellite beams here, but so as I mentioned earlier here, due to the frame-based precoder of the satellite communication, message of the users in each beam or each group will be encoded by the single code word and transmit over the air as a kind of multicast transmission. So here, the private message S1 refer to the multicast message for the beam 1 by encoding all the users in the group 1 into the single code word. Okay, so in the meantime, the partial of the multicast message can be transmitted by the part of the common message, as see here. So here, instead of transmitting M beams, M+1 beams are transmitted over the air, right? So with this, we can define the rate expression for some beam, the M's beam, right? So which is the sum of the common stream and private stream. So it involved two different minimum functions. The first minimum function comes from multicast rate. So as I mentioned, this now we are the frame-based transmission. So its private message should be decoded by all users belong to some specific beam. So yeah, we should come up with some multicast, the minimum function here. And also for the second minimum function comes from the common rate constraint. So of course, the common rate should be greater than all the common actual rate of the whole user in this network. So what we want to do here is to optimize private and common precoder, including power. So here, so this paper, yeah, try to solve to maximize the maximum fairness, which is the mean of the rate of the beam should be maximized among all the multiple co-channel multicast beams. And here is a constraint. The first constraint is come from the common message, the rate allocation. The second one is the per feet power constraint. So so this is comes from the individual high power antenna element, so-called HPA. So high power amplifier, HPA, to prevent the power sharing among the antenna element called the feed, right? So people in satellite industry are very cautious about efficient use of the power. So here we don't usually play with some total power constraint. Later we have a per antenna power constraint or per feed power constraint in satellite network design. And the last constraint is come from non-negative rate constraint. So they try to solve it using some WMMSC types algorithm with a combination of the sample approximation and sample average approximation method here. But I'm not going to details here due to the time limitation. But yeah, we can check the result here. So this is a simulation result. So here we have 7 beams and 14 users, and 2 users per beam should be allocated. So it's quite uniformly distributed. So here is the rate splitting and no rate splitting for the blue curve. And so in case of perfect CSAT, which is shown in the solid line, so the red curve should be rate splitting should be much higher, get a much higher performance than no ray splitting. So here, no ray splitting refer to the classical multi-user linear precoder called RSMA. So split of the message here, yeah, enable you to manage interference between all the different beams much more effectively. Even in case of the imperfect CSIT, also, yeah, you can check that ray splitting perform much better. And so another baseline here is full color strategy. So where so 4 different beams use the different frequency, but due to the non-efficiency of the frequency spectrum, it decreased the whole rate, not only for the perfect CSIT, but also imperfect CSIT. Okay. If you look at the right side of the figure, which is the effect of the CSI imperfection, if you see the x-axis from the left to right, so perfect to imperfect CSIT. So the gain of RSMA, the red one, is getting increasing as the quality of CSI degraded. So this is because because of the robustness of the RSMA in the presence of the CSI error. And also there's another example of so loss of the per antenna constraint, right? It's not quite big enough compared to, total power constraint. The TPC is total power constraint as in our kind of constraint in terrestrial network, and PAC is per antenna constraint. But you may see that this loss is marginal, so it's not a significant issue. And also, if you look at the hotspot scenario, so it's not uniformly distributed, and so 8 users on a center beam and 1 user in each in the other 6 beam. So which is quite imbalanced between a rate in center beam and other side beam. But still, in this case, also it has a very good performance of the RSMA over other existing one. So the next scenario is when we have the integrate a terrestrial and a satellite network called integrate satellite and terrestrial network called ISTN. So from the satellite, multi-beam multicast transmission are done, and in each beam, of course, there are multiple satellite users. But on top of that, so within this is the one coverage, the one beam coverage of the satellite. But within this coverage, you might have a terrestrial network. So some users here are served by the terrestrial base station, but the other users outside of this terrestrial coverage are served by satellite. And we think of aggressive frequency reuse. So they share the terrestrial and the satellite. They use they share the frequency resources. That might induce severe interference, right? Because the satellite usually cover a very large the coverage. They might cover lots of many terrestrial coverage. So they might, if they don't manage interference very well, then maybe it have a very bad, even the bad impact on a terrestrial base station's performance. Okay. So it's also the Bruno's group also proposed the RSMA based this ISTN design. So they come up with 2 different levels of the integration. It's like exactly same classification in the comp scenario for the 4G LTE. The first one is coordinated scheme, which provide a CSI of the global CSI. It doesn't require data sharing among the different network. But on the other end, cooperative scheme, it's required both CSI and data sharing at the gateway. Of course, it brings out a lot of burden for the data sharing. So in our cases, yeah, we just focus on coordinate the scheme. And also we come up with the new design of the ISDN called coordinated RSMA. So coordinated RSMA try to manage interference in and between both satellite and terrestrial network without data sharing. And we want to come up with the optimal resource allocation to manage interference by rate splitting. So it's a combination of the multicast and unicast for the terrestrial network, right? So satellite will perform its own rate splitting for the multi-group multicast to handle interbeam interference here. But on the other hand, terrestrial base station also perform another separate RSMA for the multiple unicast for the terrestrial network to manage inter-user interference here, right? But here is very good observation that there's no interference link between terrestrial base station and satellite user. Why is that? If there exists this link, the motivation of the satellite users are missing. The why they have to connect to satellite if they have a link from terrestrial base station, right? So it's naturally assumed that there is no interference between terrestrial base station and satellite users, but still there are interference between a satellite and terrestrial base station, right? So in previous work, they don't actually they just treat this interference from between satellite and the terrestrial users are just as a noise, because they assume the geo scenario, so this interference not very strong enough. But in our case, we also have to consider this interference between satellite and the users for in case of EDIO or MEO or cases with very lower altitude. Okay, so so we want to come up with some joint design of satellite communication and terrestrial network, not only handling intra-network interference, but also inter-network interference between satellite and terrestrial users. So to do so, we have to review the Han-Kobayashi scheme. So Ledi, it's proposed in 1981, but it's a very well-known and also best-known observable scheme for the interference channel. So where there are two users and two transmitter and two receiver, and each transmitter want to convey its own message to corresponding receiver without any data sharing between a transmitter side. So here also transmitter split its message into two parts, common and private here. So both common message should be decoded at all receiver. So the rate of the common message should be intersection of the two MAC channel here, right? MAC channel at two different receiver actually. So but a common message for the second users and first users are not intended for the first and second receivers. So they have to ignore those common messages respectively after the SIC, right? So why we come up with a common message here is for the purpose of the better interference management, right? So the how to optimize the power or common or private or how much gain we can have is shown by shown by David Shesh group in 2008. So the key idea was they just adjust private power so that interference is received at noise level at other receiver side. So private power should be reduced to the noise level at non-intended receiver. So for the very strong interference channel, very strong interference channel, the private message should be very small. So in other words, most of your power should be going through the common stream. But if you have a very weak interference channel, then your private stream should have most of your power. And medium interference channel, then yeah, you have to balance the power between common and private. So with this, some design criteria, yeah, they show that they achieve the Gaussian interference channel capacity within 1 bit. This is a very good the result for the interference channel cases. So with this, we come up with the super common message to handle inter-network interference. I mean, from the satellite to the terrestrial base station. So we adjust power allocated to the super common part such that inter-network interference between satellite and terrestrial is within a noise level. So on top of that, we can apply the separate rate splitting multiple access here, a satellite and terrestrial base station. And this super common message are not intended to the terrestrial base station. So after SAC perform, then we can, I mean, the terrestrial base station, terrestrial users should be ignored, right? So this is a basic concept of our proposed one. So we can, yeah, we can formulate some transmit receive signal, but only the difference is the super common message, and we can define. So here the cellular user denoted as the CU, and SU is for satellite user. Okay. So we can, I think, yeah, we have 5 different message. The first one is common message to handle the inter-network interference. So it can define a super common rate. The second one is a satellite common. And third one is cellular common. And fourth one is satellite private. And fifth one is cellular private. So with those combination, we can come up with some rate calculation. So NS beam rate should be the sum of the part of the super common message and satellite common message and private multicast rate. And also the NKTs, the cellular user rate, should be sum of part of the cellular common plus the private cellular rate. Okay, so with this, we want to maximize the minimum rate of all users in network. So in the satellite users, including the satellite users and terrestrial users. So problem is, I mean, problem we have is non-convex. So where optimal solution is challenging to obtain. So efficient solution can be obtained by employing some successive convex approximation technique to reduce complexity and make the problem more tractable. So we apply some epigraph form and series of some introducing a slack variable of, let's say, INR, and also to combat some in the form of the convex minus the difference of convex functions. So we apply some first order approximations and apply for the successive convex approximation like this. And also to make low functions more more non-sensitive to the, in the platform of the CVX, we also approximate log function to the second order constraint like this. Yeah, finally we got some in the form of convex, and then we can solve it very efficiently in an iterative manner with the CVX tool. So numerical results confirm the significant performance gain over existing RSMA and other conventional multiple access. So the first, the green one is SDMA OMA. So where the satellite and terrestrial network use a different frequency, and each satellite and terrestrial base station use SDMA. And RSMA OMA is also, it's separate the different frequency into two parts and to avoid the inter-network interference, but each satellite and terrestrial base station employed RSMA. So it's a little bit better performance. And those upper three curves are for the ISTN. The first red curve are represent for the SDMA for ISTN, where the interference are all shared with satellite and terrestrial. And sky blue one is the performance of our previous work, where the interference between satellite and terrestrial network is treating as a noise. And blue curve are the performance of our proposed one, the recent proposed one, and the gain from the fact that the use of the supercommon message can mitigate inter-network interference as much as possible. So, and also, yeah, we leverage rate splitting behind that to manage interference between intra-network and inter-network. Yeah, between the satellite and terrestrial network. And also you can realize that the gains, the performance gain are getting larger when altitude of satellite is decreased. So in that case, of course, the inter-network interference from the interference from the satellite to the terrestrial user should be getting large because the altitude is getting lower. So our proposed one efficiently handle this interference. So the gain is getting larger and larger as especially for lower Earth orbit cases, right? And also you may realize that SDMA for ISTN has a quickly saturate as altitude is getting lower and lower. So yeah, you may wondering why RSMA does not have that saturation, why ISTMA has. So we actually analyze it, why it happened. So so usually the satellite users rate are the bottleneck cases, usually due to the very bad channel state of the satellite and satellite users. So as the altitude or the satellite is getting closer to the ground, of course the satellite rate is increased a bit. But at the certain point, or the beyond the certain point, they might not have the gain. Later, they have a very harmful effect to the satellite or terrestrial user because SDMA doesn't have a good chance to handle the interference, right? So in this case, yeah, we analyze this by looking at some example. We realize that the satellite power should be decreased, although they have to avoid some inter-network interference. So they to lower the strength of the interference, satellite form a precorder with low power. for in case of SDMA cases. So they just keep they have some saturation here. But the RSMA cases, they have a better capability to handle the inter-network interference or even inter-beam interference between the multi-beam cases. So they might not have to decrease the satellite power and when the satellite altitude is getting lower. Okay. And also as number of users in each beam increase, of course, the multicast rate constraint should be more getting a more higher. I mean, the max mean difference rate should be decreased due to the multicast traffic. But still, I mean, the proposed one, the blue one, have a much better performance than existing RSMA or SDMA or ISTM. And regardless of the CICT error level, the proposed one can perform very well compared to other existing schemes. Okay. So now, I want to discuss some possible object function for satellite communications. Of course, you may consider sum rate maximization as in conventional multi-user MIMO, but the solution might not be proper in terms of coverage extension. They might just select the one best beam, so which is not a very proper solution for the satellite communications. And also, as in our work, you can also think of max-min problem. But on the other hand, for some service flexibility to satisfy some heterogeneous demands over the time or the geographical region would be required. So the traffic-aware rate maximization or rate matching problem would be very promising. So our K-hat is QS of the kth beam, and RK is ultra rate for the kth beam. So they wanna match up with they wanna match up of their ultra rate to the QS with some limited power satellite. That would be very interesting research direction. And before conclude talk, I'd like to advertise some event I'm co-organizing. So at WCSC 2023 conference, I'm going to give a tutorial on Internet of Things, space things with my colleagues here. So if you're interested, please join us. So we're happy to see you in Glasgow as well. So and also you already know about this special interest group website. So to conclude, we discuss main signal processing challenge in satellite communication for 6G. So we introduced some robust and flexible beamforming design for satellite communications. With this, I conclude this talk. So I'm happy to answer some question if you have. Thank you.
Thanks a lot, Wonjae, for the nice talk. Yes, we are open to questions. I see that we don't have a question in the chat, so you're welcome to raise your hand and directly ask a question, or like drop a line, and I will forward this question to Wonjae. So maybe while other think about questions, so I might start with one, Wonjae.
Sure.
In one of your last slides, you talked about different objectives, right? So I wonder, in particular, if you look at the sum rate, do you expect that the gains you have shown us are going to be at a similar level, basically, as as you have shown for the max min fairness rate?
So usually the multi-beam multicast scenario is quite interference limited reason. So if you think about some kind of interference limited reason, if if you try to find a solution for some ray maximization, you just give up some of the worst beam and then focus on just a few beam. So in that case, yeah, the solution might be totally different. I think this is not a proper scenario we want to expect for the NTN. So yeah.
Okay. And maybe like somehow related to this. So you have considered an overloaded system.
Exactly.
So,
yeah.
I guess for the scenario you're looking at, basically this is basically appropriate. But you know, given that everybody's talking about massive MIMO, more or less everybody. So I was wondering, in particular, in the like setups you have looked at in the last part of your slides, basically where you have those joint, basically terrestrial and basically satellite users. So have you investigated the impact of antennas basically on the performance here and also on the benefit on RSMA?
Yeah, so for me, I mean, so some in literature also someone also look at some the massive MIMO is employed in the satellite setting. In that setting, yeah, it's of course it's the opposite cases. It's not overloaded cases. It's underloaded cases in which the number of antenna is much larger than number of users. So I'm not have looked at these cases because still, I mean, there are some lots of limitation in number of antennas at the satellite because of the power. So yeah, now I'm just look at some underloaded cases where number of users in network is much higher than a number of antennas. But of course, yeah, so the massive MIMO setting would be very promising for this work as well. Yeah.
And maybe last question from my side. So far, you assume Gaussian signaling in your analysis, right?
Exactly.
Okay, so do you like what do you expect, basically, if let's say we go, you know, to finite constellations where, you know, because we have to decode the signals, we have to cancel interference.
Exactly.
So what is? I guess there will be like a drop in the performance, right?
Exactly. Yeah, I think, but that would be also very the important research direction because it's I mean, because for the aerial cases, it's the channel should be move very fast, pretty fast due to their movement. So maybe we cannot have a very long block. So of course, it's very worth to look at finite block lengths or constellations, etc. Yeah.
Okay. Yeah. Thanks. Yeah, I agree. So any further questions, comments? This is your chance.
Yeah, I think there are one question here.
Yeah, there's one question.
Yeah.
From Jayup Seong. So the question is, why performance gap between proposed one and coordinated schemes occurs, although the satellite user gets minimum rate? So
yeah, I mean, maybe he is asking the gap between these two. So yeah, as I mentioned earlier, because we introduced a super common message so that it can efficiently handle inter-network interference, especially for the interference from satellite to the terrestrial users. Yeah. So for the previous work, just consider that inter-network interference as a noise. But our case is we proactively handle this interference so that it's the interference is reduced to the noise level. So yeah, on top of that, so we can manage the interference very well. So especially when interference is very strong, this gap is more visible. Yeah, when kind of the geo satellite cases, it's there is no gap because there is no gap. Yeah, because there is interference level is very limited. So treating interference noise is better. Yeah, it's the optimal solution. So it's so Han-Kobayashi scheme is bridging the bridging the treating interference noise and decoding interference. Yeah. Thank you for your question.
Yes, thanks a lot. So I don't see any further questions. So then with this, thanks everyone for attending the talk. Thanks Wonjae for this nice presentation.
Thank you.
As noted by Anup, the slides and the video are available on the website. You also put a link to the website, basically. So please, everybody, basically have a look and then enjoy the website, basically. Yeah, with this, thanks a lot. That concludes the talk. That concludes this session, basically. Take care, everybody. See you next time.
See you.
Thank you, Professor Sitskin, for hosting the talk.
Pleasure.